All right. Our next presentation is Mobile System Sideband GPIO Minimization and Secondary IPC Messaging using the MIPI VGI or Virtual GPIO interface. Our presenter is Lalan Mishra of Qualcomm and Satwant. Satwant may or may not be able to sneak back over from the other track. Lalan Mishra has over 23 years of design and innovation experience in the field of wireless embedded systems. He's currently with Qualcomm as a senior staff engineer in the advanced connectivity and multi-radio architecture. In 2012, Lalan conceived the idea of Virtual GPIO Interface, or VGI, which is now in the standardization process in the MIPI Reduced Input-Output Work Group, or RIO. This work group is chaired by Lalan. He has also over 45 active inventions to his credit. He holds a master's degree from UCSD with specialization in wireless embedded systems. Please welcome Lalan Mishra.
Okay. Thanks for this nice introduction. I would go, my friend Satwant, by the way, is not with me, but I will try my level best not to make you feel his absence here. So the problem that we are going to, primarily the agenda for the next couple of minutes is, we will take a very important problem that we all are trying to solve in the industry. And we'll see that, how this new simple concept is going to help solve that problem. And what this really architecture, this VGI architecture really means, where it is supposed to be used, and once it is really used in place, what kind of benefit one can expect. Because all of you who are developers here would always try to see in light of, if you have any benefit or not. If you really don't have any benefit, then it really doesn't make any difference to you or no sense to adopt it. So the main focus is in terms of showing you the benefit so that it can bring some interest in your mind and why it should be the right candidate for your next design. And at the end, we'll see, we'll take definitely any question that you may have. So let's just start with this connectivity expansion trend. What you're seeing here is that if we see a typical mobile handheld system, I'm taking this example primarily from the MIPI background here, where the focus is handheld devices. You'll see that there is a proliferation of different types of radios and other connectivity requirement. Cellular, Wi-Fi, video, docking, all kind of things. And although the wireless is a trend for future, even as you heard from Rick this morning, even to enable wireless, we need some wired connectivity anyhow. So what happens is, if we now try to see it in a little bit more detail, and this is just a representative block diagram, it may not quite exactly meet with what you may be doing, but it's a good enough representation. So what we have here is that we have the modem, which can utilize a high-speed data link, but in addition to that, we have a bunch of other sideband GPIO lines. And typically, if you count them here, I have just shown a count of like 5 for each of these instances. And you sum them up, just for one instance, it may not sound to be like a big number, but when you add them up all together, it becomes a large number. And that's where the concern happens. Typically, here at Qualcomm, as we design system, we find that we are roughly in the range of 50 or so sideband GPIOs, which is quite large. And you also heard from John Oakley's talk this afternoon that those pins come at a cost. And you want to reduce those pins to save cost, and also to save the complexity of your PCB. So the interest of pin reduction is actually coming from multiple root causes, I would say. Now, here we have tried to show you that if you take the MIPI block diagram that we have to illustrate what are the different mobile components and try to superimpose on top of it what is the number of sideband IOs that go with different domains, then it kind of gives you a real sense that, yeah, what I just told you is really making sense. So let us take a look here. Oops. So for example, the camera domain, if you see here, we have roughly 6 to 12 IOs depending on how you implement the camera. Audio codec, again, you can have 4 to 7 sideband GPIOs. Cellular modem, 3 to 10. Wireless, 3 to 10 again. And bridge chip, depending on if you have a bridge chip required, 3 to 10. Sensor hub, 4 to 18. You sum them up all together, you come in the range of 23 to 65 GPIOs. So that gives you, even if you consider the minimum number, 23 is actually quite a large number. That 23 may define the quantum jump from your one size of package, let's say 10 by 10, to a 12 by 12 size of PCB, not PCB, but the SoC package design. And once you do that jump, the cost is quite significant. And therefore, this is the key reason why addressing this problem is so important. So now if we apply the MIPI VGI, as we have shown here, you can see that each instances of those sidebands groups that we had shown in the previous diagram, they get reduced by a 2-wire interface in each cases, and therefore that's where the saving comes. So we don't completely eliminate the number of pins that we have, but try to reduce them to the minimum number possible. So one thing, of course, you can see here is that to keep simplicity had been the prime interest since very beginning in this case, and we have shown that it can be done in point-to-point. There is network configuration possible, and we'll come to that in a moment, but this is the most simplest configuration that you're seeing here. So now at a very high level, MIPI VGI is supposed to come in 2 different flavors when we talk about the point-to-point configuration. What we have here is on the top, the concept is that you can have between device 1 and device 2 a low-speed messaging channel. This low-speed messaging channel could be, for example, a UART. It could be a high-speed UART up to 4 megabits per second. And then you have a group of sideband bit bank GPIOs, and our interest is to somehow funnel these 2 groups together into one. That is all VGI is in simplicity. So what we have here is that the same thing gets transformed in this way. In one case, we have these 2 lines, which provides us a full duplex asynchronous interface. And if we have the 3 line, as you can see here, which is the 3rd line is the clock line, that gives us a synchronous interface. So asynchronous versus synchronous, you can see that with synchronous interface, we can go up to 38.4 megahertz of speed, and which is quite big. For most of the cases, this means that you can funnel in multiple UART and sideband channels all into one if you take a common clock-based approach, or you can have a messaging channel and bunch of sideband GPIOs if you just take the 2-wire approach. Okay? Now, the very first question which comes in everyone's mind is that, okay, I have been using this, people have been using I2C, for example, or some other types of interfaces. The question is that why do you not want to use that same method? What is the drawback of using that approach? So the point is that, if you use the traditional method, these are the key things that you need, typically come in place. One is that the high-level OS-based latency kicks in, number 1. Number 2, if your system is in a deep sleep mode, then just for it, in order to wake it up, you lose some time. This may not be a penalty for some of the applications, but there could be some other application where this delay could be detrimental and may not make your system work properly. So for those systems where this type of delay or wake-up latency is tolerable, we'll see that how we can funnel in VGI over I3C as well. And we have worked with our other work group here at MIPI, the I3C work group, to enable VGI messaging or IO transfer over I3C as well. But the key point to remember is that you need to pick your requirement and if your latency requirement for wake up is not very stringent, only then you go that path. Otherwise, the point-to-point is the right way to go. So now I have been using the term virtual GPIO for quite a while now, but I haven't defined it properly. So let me try to define it in proper terms. So with the help of this diagram, of course. So what you are seeing here is that we have a CPU, and let's consider this a peripheral. And in each side, we have this GPIO map that you see here. Typically, what happens is, to the software person, if we have the GPIO map, those GPIOs are mapped to actual physical pins at the boundary of the device, like you see here. So what we are saying is that to a software person, virtual GPIO should not make any difference at all whatsoever. So how do we achieve that? What we do here is that we take the same virtual, actually same GPIO map that we have here, and part of the GPIOs from this map, we say that we will not bring it to the physical pins. Instead, we'll bring it to a state machine, and the job of this state machine is just to serialize and deserialize these GPIOs based on if any change has occurred on this side. So let's say that you have 5 GPIOs for output purposes. Even if one of them has changed, it will trigger a transmission in a serialized manner from this complex, which is the combination of the VGI FSM and the physical link. Okay? So pretty much what we are doing is we are just creating a simple trick here, or a state machine, to keep a tab or keep an eye on the state change of these GPIOs and create a serialized manner of transmission of these IO states to the other side. The reverse happens when its counterpart sends something to this guy or the host. So it comes in a serialized manner. So what happens is it gets deserialized, and those IO state values are automatically lodged into the respective IO locations that we have. So essentially, if your requirement was 10 sideband GPIOs, now those all get funneled in or funneled out through these 2 pins or 3 pins like we talked about. So in summary, virtual GPIO to a software person or from the silicon design point of view is actually a real GPIO. The only thing is that it does not come to the physical pin. Rather, it comes to this VGI state machine and then gets out to the external world through a proper choice of this physical link that we have. So we already saw, so we will not spend much time here. I think it is very clear that we have 2 flavors, 2 wire or 3 wires, but both of them are full duplex. That is one key benefit. And it is not a master pooled operation like some of the other buses are. So both sides are ready to start any transmission as and when they require. There is no polling required here in this case. So that is one good advantage, because think about this. We are trying to mimic the real functionality of a regular GPIO. Do we go and do polling for a regular GPIO if we have to have some input? We don't. The external device is free to raise any interrupt any time. So we simply want to mimic that same operation here. Okay. So now what we have here is that within VGI, we saw the 2-wire and 3-wire techniques, but we have looked much beyond into the future as far as the 2-wire implementation goes. And that's why you may see that we have so many other possibilities here for 2-wire VGI implementation. But what we found is that the cheapest and best method would be to use some kind of a ring oscillator PWM approach for the 2-wire, where your device could be very, very dumb device. And if we have a PWM-based transmission, even at lower speed, it does not require very complex circuitry to decode what data stream you are sending. So PWM, therefore, is the kind of default choice here for 2-wire approach. Then we can also use UART. So if you use UART, the standard UART fabric that you may already have can be utilized for this purpose. A standard PWM can also be used, which means that you already have a running clock available. And then we introduced a new concept which we call as phase modulated PWM. And we'll see that what the specific advantage of that approach is in a moment. So now the VGI init sequence is pretty straightforward. The 2 sides are powered on, and they monitor the line status, and once they know that each side is ready, they can start communicating. first with the default header scheme that we have, and we'll see that in a moment. And later on, they can negotiate and can negotiate on different type of protocol structures as well. So this is a very, very simplified diagram that I have shown here, but much more can go beyond this level. Now let's first take a 3-wire VGI, and you'll appreciate some of the abilities of this flavor of VGI in terms of handling some of the corner case conditions that we may have. So what we have here is a common clock source, but what you see here is the top line is the clock which is being used on the transmitter side, and the bottom clock is actually the same clock, same instance of clock, but being used on the receiver side. So on the transmitter side, we are shifting out the data on the falling edges of the clock, and on the receiver side, we are latching in the data on the rising edge of the clock. So ideally, let's say if there was no clock skew available, ideally each bit will get sampled right at the center position of the bit that we have. And that is the perfect ideal case, no problem at all. So we did a lot of analysis in terms of the clock skew and everything, and we found that, without any problem, even if the trace length at the PCB is like 12 inches long and running at 65 megahertz, still we don't have any concern. We have a setup and hold time margin of, actually 2 nanoseconds. So that doesn't give us any problem at all. And like I showed you in the beginning, that for the VGI spec right now, our target is 38.4 megahertz. So really there is no problem at all from these type of signaling point of view. Now the interesting thing is the ability of decoding or finding out some of the corner case conditions. So one of the corner case condition is to know if the master has failed. So what happens is, if the master fails, the receiver thinks that a valid data packet is coming, but once it does not find the stop bit, because this bit value position is also a value of 0, it knows that some catastrophic condition has occurred. So these kind of things, meeting these type of requirements, is normally not possible with a standard bus protocol based approach, and this is something that 3-wire VGI solves very efficiently. So now let's show you the approach that we can take with a traditional UART. So traditional UART with flow control can utilize 4 lines that we have shown here, TX RX pairs and the RTS CTS pairs. What the trick we have played here is that the flow control based line that we have can be combined with the TX and RX line pairs, and therefore once we reduce it to 2-wire, it becomes the right candidate for 2-wire VGI interface. Now one question which comes with UART is that, in case of VGI, we have the frame length running to a variable length of bits. So how do we take care of that? Because as you know, for UART, the longer the frame is, more accurate clock you require. So to address that issue, we have the concept of intermediate stop bit, and that helps the counter reset every couple of bits time, like 4-bit example has been shown here. So that way it allows you to keep the frame length as long as you want. Typically we are bounding it to 128 bits maximum. So now to the phase modulated PWM, what we have done is a very simple trick with traditional age-old PWM. We have combined a phase operation or phase modulation with the traditional state modulation or the duty cycle modulation that you have here. So with that combination, what we have done is we have created 4 symbols in the same time slot. So because in one time slot now you can combine 2 bits, effectively what happens is the transmission time gets reduced to exactly half. So when you have requirement of very high speed communication, this could be very, very useful. And this concept, by the way, could be utilized at other places like PCI 6 sideband signaling too. And if there is a strict timing requirement, this approach could be of immense help. So phase modulated PWM therefore cuts the time into half and is of a primary interest for VGI. Now here we have some illustration for protocol. You can see that we are using a very simple protocol structure. We have only 2 function bits in its simplest form, of course, I must say that. Only 2 function bits in the header, and then we have a bunch of bits which can carry either IO state or messaging information. And these explain you that, whether it is an IO state coming or a message coming, and some programming options are also built in here. This is a more evolved approach where it does allow some level of networking option as well. And you can see that the header, therefore, the complexity of the header has grown because now it is from 2 to 3 bits. We have yet, as it evolved, as VGI evolved, we have even more complex headers which can be utilized based on the requirement. And here you can see that we have up to 10 bits of header. With the 10 bits, it allows actually virtually unlimited number of protocol implementation and also error detection and error correction capability. Okay, so depending on what your requirement is, you would end up either picking up the simplest form or the most complex form. This is just an illustration to show you that we have this extended Hamming code based header to recover from any error possibility that may be there. And if you study this carefully, we have at least 2 RFUs shown here, but also we have expansion capability, which means that at the expense of adding more bits, we can extend the protocol for future, and we have tried to do a future proofing in this manner as well. So now this is an illustration for VGI network. So initially we started with VGI point-to-point. Now with the complex header structure that you saw, it is possible to have some level of networking support. But please notice one thing here, that each of this network is not like multiple devices coming on one physical line. It is, for any time, it is a point-to-point multi-node network basically. And this is the kind of scenario which could be applicable for, let's say, PCI interfaces, where also we have some sideband signal and can be solved with this approach. Now, remember I said that when timing is not a critical requirement, then you can bundle VGI or put VGI behind I3C, and this is exactly the scenario we have. So we are taking VGI, and if you have I3C with additional need of sideband GPIOs, you can include VGI in this manner, where VGI comes into the host side and each of these peripherals and takes care of the sideband consolidation. This is already approved with our work with the I3C work group, and it is part of the standard. So now comparing with VGI, this information comes from courtesy John Oakley, our friend. So what he has shown here is that how does it compare with other bus-based approaches. So you can see that with VGI, for example, you can be symmetric control, but take, for example, UART. You need a reference clock. You take other approaches, so you can see the comparison, how VGI compares with other things, other types of interfaces which are available. And then as a takeaway, this is a very high-level takeaway of this comparison. What comes down here is these points, that with VGI, we have the symmetric control approach, and initialization can happen from either side. No master, no slave is the main key point here from this slide. Now, clock comparison, we already mentioned, so I will skip to this real quick, but again to remind you, for MIPI VGI version 1, we are targeting maximum 38.4 megahertz for the 3-wire interface. Now, up here is the scenario. So let's say that while you are adopting and you don't have the actual implementation on both sides, how will you take VGI? So that's where the role of FPGA comes in. So let's say, for example, if you have this implementation scenario, which is a full VGI adoption, you don't care about anything. But take, for example, this case, where you have VGI on this side, but you don't have VGI on this side, which means that you can have a small FPGA in between, which can instantiate VGI up here, and then the two sides can talk. So we have taken the other two scenarios, where VGI is missing on this side, and in this case, VGI is missing on both sides. So actually, we did some prototype on Lattice's FPGA for VGI almost 2 years back, and it has been shown to work just fine without any problem. So now in summary, therefore, sideband GPIO, as we talked about, is a big problem. And I showed you with real example that the number could vary in a large range, 23 to 65, based on the typical example I had picked up. And MIPI VGI is primarily targeted to reduce the number of those sideband signaling and also absorb a low-speed messaging over this VGI interface. It can come in two flavors, 2-wire or 3-wire, and it has no real concept of master or slave. Both sides can initiate any messaging from each other side. For certain applications where you are not really concerned about wake-up latency, or even if it is a few milliseconds, I3C VGI is a very promising flavor, where we put the VGI FSM behind the I3C engine, and it takes care of additional sideband that you may have. It is important because you don't then require multiple instances of VGI on the master side. Because if you have one I3C VGI, you can take care of multiple peripherals sideband requirement at the same time. And in terms of the spec, we are working hard, and we hope that for adopters, we'll have at least some well-reviewed draft version available. But I won't talk on that much. We are still working on it. But we are in good shape there. A lot of technical discussions have happened, and we are on good footing for now. So with that, I will stop here and take any question that you might have. Okay.
All right.
Thank you very much.
No, I actually have a couple questions.
Sure.
In a 2-wire interface, how are you dealing with the power of your receiver always being on to be able to see the transmitter? Or is the receiver on? What is kicking on? What's kicking on the receiver to make him wake up and know that there's traffic coming?
Okay, so for the 2-wire case, then we'll have to ask that in context of which flavor are we talking? If we take, for example, let me go back a moment.
Yeah, there you go.
I'll take this example here where we have right here. So if we take, for example, the case of UART, for example, it is a 2-wire UART, and it is expected in this case that both sides has the oversampling clock running, let's say the peripheral, and if it has to send something, it is not dependent on the other side to send it any clock. It can start the communication at any given point of time. If it is a ring oscillator PWM, then what happens is the moment you start sending the data, the other side, based on the edges of the PWM stream, it triggers a ring oscillator, which then creates a clock stream to oversample the incoming bit stream and decide whether the pattern is a value of 1 or 0. Okay.
Okay.
If we have the PM PWM, so PM PWM is a slightly, we saw the advantage that it cuts the transmission time into half, but then it does have a requirement of initial synchronization. So what we do is we take the initial first bit time to synchronize the two sides. But the requirement of the clock, again, is not very pristine required, okay? Right. Pristinity is not required here. You can have a very crude clock as long as you can decode whether the high portion and the low portion of the PWM is, as long as you decipher the duty cycle, you will know whether it is a value of 1 or 0.
Where I was going with this was, how does this affect the low power states or battery requirements for having to have the devices kind of always awake?
Yeah, I'm coming to that.
Okay.
So we did a very thorough analysis on that. And we found that given the process geometry that we have, even if we have, let's say, to initiate the initial communication, on the two sides, let's say you can have some clock running so that you start the communication. But then VGI feature does allow for the clock to transition to the high frequency mode without any glitches in coming into picture. Okay. So now if we take, for example, again, I'll have to take each of these cases. So let me take ROPWM. The impact of ROPWM based clock while you are doing nothing is actually 0 because no clock is running there. Okay. And the impact is only when you are transmitting some data. What we found is that the impact of data transmission from power point of view is coming more from the link versus actually on the silicon for RO PWM. Because the capacitance that you have on the link is consuming much more power than what this ring oscillator is actually demanding.
Okay.
So we presented that data to another forum because we did all these analysis with PCI SIG as well as part of our what we call a liaison agreement with them. And I presented all this data to them, and most of the power goes into the link, surprisingly.
Okay. All right.
Okay. Any other question?
All right.
Hi, John.
Okay, hi. So one thing about the wake up also, if I can say something. Normally for the power down case, I think that was the question you also asked. You would actually have since nominally you're high, you can actually detect that it exists or not exist by the fact that it's high versus low, right? So that's also part of the wake up, correct?
That's right.
So you can actually detect from either side that the other guy is awake or not. And then I think in the protocol, you put something else in there as well.
So for wake up, it is high to low. There is one more thing that we have put, and we discussed it in, I think, New Orleans meeting. So let me briefly describe. It is not shown here, but just to give you. So what happens is, we also want that in VGI, let's say if the master is sleeping and the host asynchronously sends something, how do we guarantee that it was not lost in the air? Okay. So one provision we have that, and I think in the MIPI spec we don't want to make it mandatory, but based on how people want to implement it, the trick is that the two lines that you have there, let's consider the UART mode of VGI. We implement a switch there. So if you are the master and you are going into the sleep mode, then that switch is automatically closed. So it provides you an echo back path. And the transmitter on the other side, when it sends something, it gets its own echo. And based on the echo signature, it knows that, yes, it is not my counterpart's message, but it is my own message. And therefore, I must wait for retransmission. And then we have defined at least two different types of wake-up scenario. But at the end of the day, we have guaranteed that no message is going to be lost in thin air. And the two sides will always be able to talk to each other. Okay. Yeah.
So, what about debugging? Usually we used to probably mind
Uh-huh. So good question. So I think for debug, what will have to happen is, just like any serial interface, whether it is UART or I2C, you'll have to capture the entire transmission bit pattern. So it won't be a very straightforward debug because of the serialization nature. Some entity has to grab the data, capture it, analyze, and present it. So I'm sure that once VGI is a published standard, the debug guys will jump right into it and create their own VGI specific debug tools. Yeah.
Any other questions?
Okay. Thank you very much.
Thank you.